Okay, so we're now going to go ahead and talk about escape velocity. So what I want you to think about is, what do you think of the word when you think of the word escape? So I think of like get rid of, like have no influence of, like all those things come up when I think of escape velocity. So in physics, our definition of escape velocity is, is the velocity needed for an object to escape the gravitational pull of a planet and never return to that planet. So let's think about it. If you're just tossing, like, let's say a tennis ball on the surface of the Earth, can that ball, with whatever velocity you throw it with, escape Earth? No, because, and how do you know? Because the ball comes back down, so it is not escaping. So the velocity has to be big enough that you throw something for it to never return to that planet. It just escapes the gravitational pull of that planet. So it has to be pretty darn fast. So let's go ahead and talk about how to derive the equation for escape velocity. So let's look at this. So we are now on Earth. So we want to figure out what velocity we need to, so I'll call it velocity escape, for something to escape the pull of Earth and never return. So I'll go ahead and draw it like out here in space. Let's say it's like infinitely far away. Okay. So let's see. We want to find that. So oftentimes if you want to find velocities, and if things are changing positions, energy conservation is a great bet. So let's go ahead and look at what type of energy it has at each of these two positions. Okay. So right here at V escape, what type of energy does it have there? Well, clearly it has kinetic energy because it's moving. Let's see what else it has. It also has gravitational potential energy because it is some distance from the center of the Earth. And again, we're using our negative g, m1, m2 over r for ug because we are dealing with like the acceleration due to gravity is changing as you go different distances above the surface of the Earth. Cool. So now let's go ahead and look at the object once it's escaped completely. So go ahead and take a guess. How much UG does it have when it totally escapes, and how much KE? Okay, so if something is totally escaped, the UG, it should have no gravitational pull. The UG is going to be approximately 0. One way I look at it too, if I write down my equation for UG, and if we get to R equals infinity, so if the bottom is infinity, any number divided by infinity is going to be approximately 0, and I can write that out a little bit better. So that is also a mathematical way to prove that. So that is approximately 0. Cool. And then how much kinetic energy does it have when it's all the way out there? Well, if you escape somewhere completely, you do not need to be moving at all. Sure, you could be moving, but you do not need to be moving. So we'll just assume that KE is 0. Cool. So now let's go ahead and set up an equation that explains this. So we have at the first position, so again, those are two positions that we're comparing. The first position, we have UG plus KE equals the other position, essentially UG plus KE, but then we'll go ahead and plug in the numbers for those. So UG again is negative GM. So in this case, M1 is the mass of the shell. Let's see, mass of shell times mass of the Earth over, we are just on the radius of the Earth. Just to start, we're on the surface of the Earth, so that's the radius, plus 1/2. Let's see, what mass will I use? It's the shell moving, so I'll call it mass of shell times velocity squared equals UG, we set at 0 when we're infinitely far away, and KE, you don't need to be moving to escape completely. Cool, and we're solving for V escape, so let's go ahead and solve for it. So let's see, it looks like I want to add the UG to the other side, so we're left with times V escape equals what? G, mass of shell, mass of Earth over radius of Earth. Cool, let's simplify this. I forgot my squared for V escape. Silly mistake, so easy to do, don't forget that. Mass of shell, cancel that out. Let's see, I'm solving for V escape. I can multiply both sides by 2. And let's see, I am left with V escape, and then I can take the square root. So that's going to be what? 2g mass of Earth over radius of Earth. So that is my general equation for V escape. Let's go ahead and plug in some numbers just to see what it is on Earth's surface. So G is going to be 6.67 times 10 to the negative 11. Oh, I almost forgot about the 2. Include the 2. I just put it in a slightly different order. That's fine. 5.97 times 10 to the 24th is the mass of Earth. Radius of Earth is 6.38 times 10 to the 6th. Cool. And I get 11,172 meters per second when I plug this all in. Cool. Well, thank you for, oh, no, no, we're going to go over one more together. One that is kind of pretty similar on AP Physics exam, a typical multiple choice example with just variables. So last one, and then you're out. Okay, so let's look at this one. So escape speed for a rocket at Earth's surface is VE. What would be the rocket's escape speed from the surface of a planet that is twice Earth's mass and the same radius as Earth? Okay, so we're trying to find escape speed. First thing let's do is let's go ahead and derive the equation for escape speed. So again, we've just done it, but the escape, so again, here it has KE and UG. Once you're all the way out to the middle of nowhere, there is the KE is going to be 0, and the UG is going to be 0. Cool. So it's going to be negative G, mass of object, whatever it is, mass of Earth over radius of Earth, plus 1/2 mass of object, V escape squared equals 0. I solve for V escape all by itself, and I get square root of 2G mass of Earth over radius of Earth. Cool. So we'll use that equation to compare. So, okay. So, and again, that is on Earth's surface. So on Earth, I'll go ahead and write V escape is square root of 2G ME over RE. Okay, so now we're looking at another. Okay, so I'll call this the new planet. So this new planet, it is going to be, so it's twice Earth's mass and the same radius. Okay, so I'll call it V new is essentially what we're doing, and we're going to compare, see what that escape velocity is going to be. So it's 2G, instead of the mass of Earth, it's twice the mass of Earth over same radius. So I'll just call that RE. Okay, so I essentially want this new V to be in the same terms of V escape on Earth. So I'm going to see if I can manipulate this to figure this out. So I'm going to keep, what I want to do is I want to keep, sorry, I was moving things around a little bit. I want to keep the 2G ME over RE under the square root. So I want all this stuff to be under the square root. So I'm essentially stating this, and this. So what do I need to pull out? It looks like to me I need to pull out a square root of 2 from there. So then I'm just left with 2G ME over RE. And again, that's because this whole thing that I highlighted is just V escape on Earth. Questions on that? Well, I guess we can't really ask questions, but shoot me a question if you have it later. So again, that whole thing right here is just what our original one. So V escape, and that is going to be our final answer. Okay, so this is something I should have done at the beginning, but we're going to go back in time and do it. So let's think about it. From the very beginning, if the mass is bigger, so the mass is bigger, and the radius stays the same. So if you're essentially increasing mass, radius stays the same. What's going to happen to escape velocity? That looks like it'll make escape velocity increase. So I know it can't be D, can't be E, and can't be C. So I'm just left with A and B, which is lovely, a 50% shot. I think it's a great idea to think about what you can cancel out. Yeah, so that if you're in a pickle, you can at least, take a good guess. So we are left with B as our answer. Great. Thanks for watching.